Hello everyone, welcome back to this Physics 80 live stream. This is week 4, and this week we're going to move on to circular motion. So we've talked about kinematics in the past for a couple weeks, moved on to Newton's laws, and now we're going to do a chapter that's kind of a standalone chapter. It just finds its way, in the syllabus at this point in time, and it's about circular motion. So it does tie to an extent to Newton's laws, specifically Newton's second law, but it's just kind of this thing that we could do later, but we choose to do now, and it has nothing to do with what we just did, really, and nothing to do with what we're about to do next. But at some point or another, we should talk about circular motion because it's not all that uncommon, and it's a very specific type of motion. So the goal today is going to be to go over the few things that we do need to know about circular motion, how do we account for them, and what do we need to use to properly describe circular motion. And then we'll do some classic problems to see how you set up a circular motion problem, and you'll find that it's pretty straightforward. There's not a lot of new things. There's hardly anything new, in fact, other than Newton's second law looks a little different, and that's maybe a little weird. So let's hop into this right here, and let's talk about circular motion. So we have just a few things that we need to talk about before we get started with problems. And again, as a reminder, this is all on slackademia.com. If you go to the study guide page, log into the free course Physics 8A live stream. You don't need to enter credit card or anything like that. It's all in there. The homework problems are in there solved. And it's just a nice container to have everything in one place so that you don't have to browse the internet and different playlists and YouTube to find it. And then if you want to get in touch with me, feel free either through the contact form on the website or through our Facebook page, and you can DM me there. So happy to answer your questions if you have any, and just feel free to reach out at any time. So, circular motion. Circular motion is an interesting type of motion. It turns out objects don't typically move in circles, not on their own, right? And we'll exclude, sure, planets and the moon and Earth and orbiting and all that. Let's exclude all of that. If you take a tennis ball and you want it to move in a circle, you can't get it to do it on its own. You could tie a string to it and twirl it, then sure, it would move in a circle, but you can't get it to do it without that additional step. And the reason is, to get circular motion, let's just draw a circle here viewed from above, you need, for circular motion, to always have a force pulling you toward the center. So before we get too deep in the weeds about that centripetal force and whatnot, here's a circle, right? Now circles are interesting in terms of motion because it turns out that the traditional x and y coordinate system that we use is not a very good coordinate system. And if you think about it, the equation of a circle centered at the origin is going to be x squared plus y squared is equal to r squared. Ugh. So to account for a circle in terms of x and y, it's not that it can't be done, it's just that it's not very easy to deal with. And so we've been used to using x and y because it's been very helpful when it comes to kinematics or even Newton's laws because, well, it defines horizontal, left and right, and then vertical, up and down. And we can break forces down into components along those directions. And it's okay because x never changes. It's always horizontal, usually to the right. Y never changes. It's always vertical, usually up. And that's convenient in that case. Now, we would like to have directions that never change when it comes to circular motion, but that's pretty hard to do because by definition, if you're moving along a circle, your direction is changing all the time. So what we do instead is we use what's called the RTZ coordinate system. Now, this, I don't know why, but nobody takes the time to define what this is as far as I can tell. I've never met anyone that teaches Physics 8A that comes up and says, hey, guess what? What we really need to talk about first is RTZ coordinate system because it defines everything that follows. So bear with me. If you've never seen this before, it's not that hard. But if you've never seen it before and you're confused, that might be why. So we need a coordinate system. And a better coordinate system than x and y is going to be the RTZ coordinate system. Now if I look at the circle from above, and this is, let's say this is a little, I don't know, you're on a merry-go-round and you're going around, let's say counterclockwise viewed from above, like this, right? And so later on, you're going to be here, and then you're going to be here. Okay, so X and Y are not good choices because they change, well, your direction changes all the time, and it's hard to account for it relative to those fixed directions. However, the RTZ coordinate system does the following. If this is you, and you extend your left arm, well, how do I do this? Your left arm toward the center of the merry-go-round, then it looks something like this, right? Your left arm is going toward the center of the merry-go-round. And then your right arm is going to go straight in front of you, like this. Okay? And then there's a third direction, which we're going to need, so we're going to define it now. But that would be the Z direction. If you look straight up with your arms out like this, if you look straight up, that would be the Z direction. And so that would be out of the page here, right? And out of the page, if we draw a circle with a dot in the middle, that's going to be out of the page. So I'm going to call this Z out of the page. And then this is going to be direction R, which is radial along the radius, and T, which is tangential, right? Which is because it's tangent to the circle, okay? Now, as you go around the merry-go-round, if your left hand is toward the center, it remains toward the center at all times. Same thing, if your right hand is in front of you, pointing in front of you, it remains in front of you at all times. So this coordinate system, the RTZ coordinate system, is a very special coordinate system because what it does is that it moves with you. Okay? So that R is always toward the center, T is always tangent, typically in the direction of motion, and Z always points, well, perpendicular to the circle. I mean, it could be out of the page or into the page, it doesn't really matter, but let's say out of the page in this case. And so as you move, right, later in time, if you're down here, again, T will be tangent, R will be toward the center, Z will be out of the page. It won't change. So that's a new concept because X and Y don't move. They don't move with the box as you pull the box to the right. It's just X and Y, they're X and Y. They're fixed. Well, this coordinate system moves with you. It is attached to you. You can think of it as your left hand, your right hand, and you looking upward being the third direction. You can think of it that way if you want, and it moves with you. But everything we're going to derive is going to be relative to this moving coordinate system. Okay, so what it means is that you do not have a choice. You must, in fact, use this coordinate system when it comes to circular motion. You can't say, oh, JK, I'm going to use something else. No, no, no. If you have circular motion, you must use R, T, and Z because everything we're going to define is going to be relative to those directions. Okay, so let's then do the following. I'll make a copy of this real quick, and I'm going to clean it up a little bit because I don't need all of this. I just want to focus on one location for now. That's good enough. All right. And this, okay, this will be R, T, and Z, right? And if you were, just for clarity, if you looked at it from this direction, right, what you would see, right, is R pointing left, Z would point straight up, right? And actually T would be into the page. Now it turns out that into the page is a circle with an X like this. Okay, so this is, if you looked at it from this direction, that's what you would see. Okay, so I'm doing that so we can visualize the direction Z, right? Because it's kind of hard to picture here. Okay, so we have three directions. In general, the most general case of circular motion, we could have acceleration along each direction, right? So we could have an acceleration A sub R along the radial direction, A sub T along the tangent direction, and A sub Z, it's hard to draw, but this is why I drew this view. I can draw it here. This, by the way, would be A sub R. Okay. Now, that's the most general circular motion you can get. And by the way, since z is perpendicular to the plane of the circle, if you have an acceleration in this direction, it means that not only do you move in a circle, but you move up along z at the same time. So that's a corkscrew. Okay. Now, we don't do corkscrews. We could, we just don't. So we do plane circular motion, meaning that it occurs in a plane and there's no motion perpendicular to the circle. So for the entire class, there will be no motion along z. We only consider plane circular motion. With, therefore, a sub z is equal to 0. Because, of course, if there's no motion along z, well, then there's no velocity. And then if there's no velocity, well, it follows that there's no acceleration because you can't, nothing changes. There's no velocity that can change, and so since acceleration is the change in velocity, there's just no acceleration. Okay. That's the first simplification. The second simplification is that there will be no acceleration along t. I'll add 99.9% of the time, because I have seen over the years a few exams where, oh, JK, we do have an acceleration along t. It's not that hard to deal with, you can, but the point is the bulk of what you're going to see will not involve acceleration in the t direction. That's just good to know. Okay, so then we mostly, I'll say, not only, mostly consider uniform circular motion. In which the speed v is constant, and therefore a sub t is equal to 0. Okay. Now, something to understand about a sub t, this is the acceleration in the direction of velocity, right? Remember that velocity is always tangent to the path. So this would be my velocity vector at that moment. A sub t is going to be what changes the velocity in that direction, right? So it's going to either increase it or decrease it, meaning a sub t is responsible for speeding you up or slowing you down. Now, if you do not speed up or slow down because you have constant speed, then a sub t is going to go away. It's just going to be 0 because you go at constant speed around the circle. However, not all acceleration is 0 if you go at constant speed, because, and this is really important, here your velocity is tangent, right? Tangent here, as you move around the circle, your speed might not change, meaning the length of that vector might remain the same, but the direction of the velocity vector changes all the time, okay? So, velocity as a vector, maybe not in magnitude, but in direction, changes all the time. That means that you must have an acceleration to change the velocity vector. So even if a sub t is 0, a sub r will never be 0. A sub r is the acceleration that is associated with the force that pulls you toward the center. And if you do not have a force point pulling you toward the center, you cannot move in a circle. It's just not possible. So a sub r is there to stay all the time. Okay. Note that, we'll just make a note here, note that v constant does not yield a sub r is equal to 0. This is really, really important because we've heard for so many weeks already that, oh, speed's constant, boom, no acceleration. Okay, yes, true, if you're talking about motion in a straight line along x. If speed is constant along x, ax is 0, goodbye. Okay, but you need a sub r to have circular motion, right? So circular motion requires a net centripetal, which means toward the center, force, and AR is the associated acceleration. And this is going to make more sense when we write Newton's second law in a second. It is the acceleration that is responsible for the circular motion, because it's the acceleration that changes the direction of velocity all the time. So it's the acceleration responsible for the circular motion. And we have a sub r is equal to v squared over r. Okay, this is really, really, really important. Okay, the acceleration in the r direction, if speed is constant, all it tells you is that acceleration is constant, but it's not zero. Now, where does v squared over r come from? It's like, well, you know, we could derive it. I actually have a video of its derivation, but unless you like mathematical derivations of rotating vectors for that matter, it really doesn't add much to the conversation. But because we don't do the derivation, you don't necessarily realize that this is an important part of circular motion. So I am telling you, this is key. V squared over r, we don't know where it comes from, but we will accept on faith that it is an acceleration toward the center, and that without it, I cannot have circular motion. Full stop. So in any problem that I'm going to be dealing with, I will for sure, at the very least, have a sub r, which is going to be the acceleration toward the center, called the centripetal acceleration. Okay. Now, I will do a problem where at is non-zero, because I do want to show you how you deal with that, and that it's not that bad. It's just that most of the time we will have at is equal to 0, in addition to, for sure, a sub z is equal to 0. Okay, so what does that lead to? Well, it leads to the following. If we have this here, make a copy real quick and bring it down here and put that in here. There we go. If we have this, then Newton's second law, N2L, is going to be the following. We're going to write F equals ma along each direction, just like we did with x and y. F net x is max, F net y is may, right? So Newton's second law is going to look like this. It's going to be F net along r is going to be ma sub r. Okay, but we just said a sub r is v squared over r. So you get F net is mv squared over r. All right. Now, that's important also to realize that that's what this thing means, because this is a weird term, and everybody thinks it's weird when you start circular motion. What's the mv squared over r? Well, it's just mass times acceleration. It just happens to be the case that this strange centripetal acceleration, the radial acceleration, is equal to v squared over r, right? So this thing is this. That's why we write mv squared over r. Now, what's interesting is that there's a direct relationship, therefore, between net force and speed. Whereas before, we had to use net force to find acceleration, and then kinematics to get velocity or speed. This is pretty interesting. You get direct relationship between force and speed, and we'll see that it makes solving actually a lot easier. Okay, so then F net t, by definition, is going to be mass times acceleration. In the t direction, that's going to be 0 most of the time, but not always. And then F net z is going to be m a sub z. That is going to be 0 because we focus solely on plane circular motion. Okay, so we could spend a lot more time talking about circular motion, showing that acceleration has to point toward the inside of the circle, and it breaks up into two components, and depending on if the speed is constant or not, there's only one component. That's all fine. I do have videos about that, and you can watch them if you want. I don't think we need that. What we need to understand is that there's something special about circular motion that requires a special coordinate system. In the context of that coordinate system, given the restrictions that we put on circular motion, because we don't study it in full-blown detail, we will have no acceleration along z, and most of the time no acceleration along t. However, there is a guaranteed acceleration along r, which is v squared over r. And that all translates, as I did here, into Newton's second law. And we just need to get good at setting up the problem with the right coordinate system, the right free body diagram, and then writing Newton's second law for the most part. The only other formula that's going to show up is going to be the period of revolution, and we can cross that bridge when we get there, right? There is a formula that you could just write down and memorize, but we'll just do it in the context of a problem because you need to have constant speed. In other words, you need uniform circular motion for the period of revolution to make sense in the first place. All right, shall we? Let's start with this guy. Now this one is a combination of two things. It's this insanely classic question, the first one. There's no way you get through Physics 8A without seeing this question multiple times, not just now, but also later, once we study solid rotation and rolling without slipping. It'll come back, you'll see. And then the second question and the third question, they kind of go together. The point was to show you that, okay, yes, sometimes the tangential acceleration is non-zero. How do we figure out what it is? So it's a bit, I put it first because, yeah, it's more complicated, but it's also more rare. So I kind of just want to talk about it, get it out of the way, and then we can move on to other classic problems. So you have a loop that is frictionless, has a certain radius r, right? And this block is launched so that it attempts to go around the loop. And we want to find the minimum speed that is required for it to make it around the loop. Okay, so, which is an interesting question because, and this one often throws students off, but let's just think this through. If you throw it pretty slowly, right, so it'll climb up a little bit, but then it'll come back down. Or maybe it climbs up a little bit more, but then it falls off because it makes it, you know, all the way almost here, but then it's not going fast enough. It falls off the track. But the point is, if you do not throw the block fast enough, it will not make it around the loop, period. If the block has a lot of speed, hopefully it's easy to convince yourself that it's going to do this. It's going to go around the loop, right? So there's a sweet spot in the middle. And the question is, well, what's the discrepancy? Like, what's the threshold between making it and not making it? Okay. Now, everything happens at point B, but the question tells you that. The question says, what is the minimum speed that the block must possess at point B so it makes it around the loop? Okay. So let's draw the block at point B. Okay, because now with circular motion, remember I have to draw this RTZ coordinate system, but to do that I have to know where I am. So if you tell me that I have to be at point B, I'm going to draw the block at point B. Okay, and then it's circular motion, so I don't have a choice. I need to draw my axes. This is going to be R toward the center. This is going to be T, tangent to the circular path in the direction of motion. Z would be out of the page. I just don't care, right? There's no motion along Z. It's hard to draw. I'm not going to draw it. I'm just going to draw R and T. But know that Z is here coming out of the page if need be. Okay, so these are my directions, right? And we want to figure out the speed that the block must possess at point B to make it around the loop. Well, let's draw the forces acting at B, on B rather, at the top here. So I'm going to extend this so that I continue to see the R direction, but I want to be able to draw two forces. I want to draw the weight force, okay? This block has a certain mass, and therefore it has a certain weight. So this is mg. And then there's also the normal force, okay, because the block is on the inside of the track, and the track therefore pushes down on the block with a force which is just the normal force, right? You could call it force of track if you want, but really it's a normal force from the surface pushing inward, okay? And so those are the forces that are acting on B. Now let's write Newton's second law. Newton's second law, the only direction that matters is R. There's no force along T, right? So everything's straight down along R. So F net in the R direction is equal to mv squared over R. Okay, now that's going to be n plus mg is equal to, I should have used a capital M there, is equal to mvb squared divided by R. Okay? Now, the difference between making it around the loop and not making it around the loop at point B is whether or not you lose contact with the track at point B. Now, that's conceptually, not everybody sees that as obvious or even understandable. It's like, what? So at point B, right, the hard part is getting to point B. Like, first of all, if you don't make it to point B, guess what? You're not ever making it around the loop, so duh. If you make it past point B, then you're kind of out of the woods because you just slide down the track, right? So cool. But at point B is the threshold. If you lose contact with the track here, then you're going to continue to move, but you're going to fall, right? And you're going to lose contact with the track and fall off the track. Now that happens if you're going too slowly, okay? Now, there's a few ways to look at it, but maybe intuitively you would agree that the faster this block goes around, in other words, the faster it's moving here, the more the track pushes on it to keep it moving in a circle, right? Because I need a force toward the center to move in a circle, and it's hard to move in a circle, right? So the faster I go, the more I have to exert a force downward to keep this thing moving along a circular path. And so maybe that makes sense, maybe it doesn't. If it doesn't, you could argue it with math. You say, look, mg is mg. That's not going away. And then the bigger you make VB, because it's the only term that changes here, the bigger n has to be as a consequence, right? So that tells you that the faster you move, the more the track has to exert a force on you at the top to keep you moving in a circle. So if that's true, it should help us understand that the smallest speed that I can have here is such that this term is equal to this term, and this one goes away. Well, when that one goes away, when the normal force disappears, it means I lose contact with the track. That is, in fact, how I describe losing contact, because the track can no longer feel the block, so we can't push on it. There's no more contact. Okay, so the smallest speed VB, we'll just call it Vmin, at B, that allows the block to complete the loop corresponds to n is equal to 0, meaning that the block loses contact with the track. And if that's the case, then I can rewrite Newton's second law, which is n plus mg is equal to m. If I write Vmin squared here over r, then I have to make n 0. Okay, now if I solve that, mass goes away, and I get Vmin is gr, which I square root, because I have v min squared. And so I find v min is square root of gr. This is called the critical speed. Right? It's such an important speed that it has its own name. It's the critical speed. It is only a function of gravity, which presumably is everywhere near the surface of the Earth, and the radius r of the loop. It has nothing to do with the mass of the block. Okay, and you'll see that this shows up a lot in circular motion. And typically it's associated with losing contact with the surface that is circular. Even if you're going around the outside of a circular bump, if you go too fast, you lose contact, and the critical speed is still square root of gr. So this is a speed that dictates whether or not you make it around the loop. Okay, so if you're going at a speed vb that is at least v min at the top there, then yes, you will complete the loop. Otherwise, you don't. Okay, now this is a super important result. You have to be able to derive it. You have to know that it exists. And hopefully you can convince yourself that, well, yes, the threshold between making it around the loop versus not is losing contact at point B with the track or not. Okay? All right, so this question is kind of a standalone question. I say that to preface the next question because the next question says, assuming the speed at point A, which is here, is equal to the speed you found in question 1, so is equal to the critical speed, which again, it's separate from the first question, which just happens to be the speed at point A. Okay, what is the magnitude n of the normal force at point A? All right, so let's just draw it out. Okay, now I'm at point A, so I have to redraw my free body diagram and my axes because that depends on where I am in my circle. Right, so if I am at point A, right here, then my r direction is going to be toward the center, like this, and my tangential direction is going to be tangent to the circle in the direction of motion, like this. Z is out of the page, I'm not going to draw it, same thing as before. Okay, and now I'm told VA is square root of GR. Okay, but that's just, again, nothing to do with the previous question. It's just we decide that that's the speed at point A. By the way, if that's the speed at point A, since you're going to slow down to make it to point B, in this particular case, you definitely don't make it around the loop. Okay, but let's just agree that's VA. We don't have to try to find a relationship with the previous question. There is none. It's just a speed that I chose because it's kind of easy to use, right? And now we want the normal force acting on the block at point A. Okay, well, the normal force is always perpendicular to the surface that exerts it, and so it points toward the center. But there's still also the weight force if we're going to be drawing forces acting on the block, and so I have mg. This time, well, it's always straight down, but this time, therefore, it's along minus t. Right. And notice, by the way, that the normal force will always point toward the center, which is consistent with what we said. If you do not have a force pushing you toward the center, you cannot have circular motion. So that is the track's job. Seems obvious. That's why we built the track, is to get the block to move in a circle. But that is the track's job, is to exert a normal force to get the block to move along a circular path. Okay, so then, can we find the normal? Well, probably. Yeah, we don't have much, right, at our disposal. We pretty much have Newton's second law. So let's write Newton's second law. And if we're going to write it, I'm going to write it along both directions, r and t. So I'm going to write F net r and F net t. F net r is going to be m VA squared over r. And then F net t, I'm going to write m AT, just to be general. Because it turns out AT is not 0 here, because there's a net force along t. Okay, but what do I get? Well, I get the following. The net force along r is just the normal. That's it. And we're claiming that it's equal to m VA squared over r. And then in the t direction, I have minus mg is equal to m AT. Okay, we can worry about AT in the next question. For now, we just want the normal. Okay, well, the normal force is easy to get, yeah? n is m VA squared over r. Okay, we said VA is square root of GR, so that's going to be m GR over R, which is just mg. Okay, and so that's going to be the normal force at point A. Now, just to be clear here, I am not saying that the normal force equals weight because of equilibrium or anything like that. This is an accident. It comes from VA actually being equal to square root GR, right? So N is equal to mg in magnitude. That's just how much force is exerted toward the center at point A because of this speed, but it has nothing to do with this force that is in a different direction entirely, right? It just happens to come out at the same magnitude than the weight force. All right, and then what is the acceleration of the block at point A? Draw the acceleration vector. Okay, so, well, let me recycle this because I can use this for this question. Now I want the acceleration, right? So maybe I can just do this, right? Let me just write this because this is kind of the generic Newton's second law. But recall that AR is VA squared over R. So in other words, we do know what the acceleration in the R direction is because all we have to do is plug in VA into VA squared over R. So that's the first component. But I am going to need A sub t, which is going to be the t component of acceleration, right? So this we said is n is equal to, we already used this, so I'm just going to rewrite it to be consistent when write two equations like I have above, but we have already used that, and then along t, the net force is minus mg equal to mat. Okay, so m goes away and at is negative g. By the way, that makes sense. The acceleration is negative. That's why you slow down on your way up, right? The weight force slows you down. Okay, so I have two components. I have AR is VA squared over R, which is GR over R, and that's G. And then A sub t is equal to, well, minus G, right? That's what I just found here. So I have an acceleration at point A, which has the following components. It has a component AR toward the center and AT downward. And they're both equal to G in magnitude, and they have therefore the same length. And the acceleration vector A at point A is going to have a magnitude that's going to be square root of AR squared plus AT squared by definition. So A at point A in magnitude is square root of AR squared plus AT squared. That's going to be square root of G squared plus G squared, and so that comes out to G square root of 2, right? Which would be in meters per second squared if I plugged in G and I crunched that number. And then in terms of direction, well, I can describe direction however I want. Maybe I use an angle. Now, I could use this angle or this one. I'm going to use this one. I'm going to call it beta just to give it a name. And you could argue, hey, look, this is G in magnitude. This is also G in magnitude. So the two vectors have the same length. So the only solution is to have beta is 45, right? They're the two sides of a square, basically. And so the angle is 45. Or you can just say, well, we just draw it out, right? And say, well, beta here is the angle defined by these two lengths here. This is AT, this is AA. And so typically what we would do is we would write tan beta is equal to opposite A sub t over adjacent AR, and that's going to give me beta is arc tan or inverse tan, same thing, of AT, which is minus G divided by G. That's minus 1, so you're going to get minus 45. Okay, the minus doesn't really mean much. It's just a factor of angles being clockwise or counterclockwise. You could just, if you just want to argue that these are distances and therefore they're positive, then you would just get 45 degrees. And you drew beta anyway, right? So you could say in words, beta is 45 degrees counterclockwise from the minus x direction or whatever, or just draw it in 45 degrees, basically counterclockwise from the horizontal, but downward like that. Okay, so hopefully not the worst problem, pretty straightforward. The things that are new about circular motion is that we have to draw the free body diagram wherever we are, right? So question 1, we were at the top here, we were at point B, so we drew it there with the axes there. But of course, when you're at point A, well, you're at a different location, the forces look different, the axes are different in terms of, now R is horizontal and not vertical and things like that. R always points toward the center, but in this case it's horizontal, not vertical, and I always have to draw where I am with my axes and my forces so that I can then write typically Newton's second law. That's the thing we most commonly do when it comes to circular motion. All right. Okay. So let's do a bit of a harder problem. This one was kind of to just get comfortable with the RTZ coordinate system and Newton's second law and things like that, but also to talk about critical speed because it's very important. This is a more classic exam question, where now we have two objects. We have mass M1 and M2 that are connected by an ideal string. There's a hole in the table, and M2 is hanging and doesn't move, right, while M1 goes around. And we want to find the tension in the string, and then the acceleration of M1, and then the speed of M1, and the time period of the uniform circular motion, in other words, the period of revolution. Okay, so let's, I'll make a copy of this just to have it, to reference it real quick, but we don't need it that much. We're just going to redraw this thing with two separate free body diagrams, right? So first we will draw the free body diagram of M1. Okay, so if I look at M1, right, just at the level of the table like that, and I see M1 here, right, and there's a hole in the table somewhere here, let's say. All right, what are the forces acting on M1? Well, it has a mass, therefore there's a weight force, M1G, but it's on the table, so there's a normal force N, and then there's a tension, maybe call it T1, pulling it toward the center, ensuring that it moves along a circular path. Okay. Now I should get into the habit of drawing my RTZ coordinate system at this point because I have circular motion. Okay, so I'll draw it here on the side so I don't overcrowd the figure. R points toward the center of the circle. There's no choice. That has to be the case. T in this case would either be into the page or out of the page, but I'm not going to draw it because it doesn't really matter. And the only direction that matters also is Z. So R and Z are the directions we see here. Okay, so note the difference with the previous problem. The previous problem, the circle was vertical. Okay, so if I draw my axes, the two that are easy to draw, R and T. If my circle is horizontal, the two axes that are easy to draw are R and Z. But in both cases I have R because without force toward the center, there's no circular motion. Okay, so that's the free body diagram for M1. And then let's draw the free body diagram for M2, and maybe I can just draw it here, right, so that I don't have to redraw something entirely different elsewhere. So this is going to be M1, and M1, I'm sorry, not M1, M2, my bad. This would be M2, which has a weight M2G, and the tension, T2, holds it up, and M2 doesn't move. Okay. Now, by the way, we have an ideal string, and the hole behaves like an ideal pulley. All it does is redirect the direction of tension. And so we have T1 is equal to T2 because we have an ideal string. All right. So what do? I want to find tension in the string, meaning I want to find T1 or T2. It doesn't matter because they're the same, right? Now, maybe I don't know where to start to find T1 or T2, and so what I could do is just write things that are true, and if I get equations, maybe I have enough of them that I can solve for tension, right? So if I apply Newton's second law to M1, let's just start with M1. All right, we're going to have F net R is equal to M1 V squared divided by the radius of the circular path is R, and then F net Z, well, that's MAZ, but that's 0 because there's no motion in the Z direction, right? M1 doesn't take off, it doesn't crash through the table, it just stays level on the table surface, so there's no motion along Z, meaning no acceleration along Z. Okay, F net R, the only force toward the center is T1, so T1 is M1 V, T1 is M1 V squared over R. Not very helpful because I don't know what V is. If I did, then I would have T1, but I don't. Okay, and then along the Z direction, it is going to be N minus M1G is equal to 0, which tells me the normal force, which I don't really need, but sure, I'll take it. You know, it's N is M1G in this case. Okay, now that's because M1 moves in a circular path, so I have to write Newton's second law, specifically Newton's second law for circular motion, where along the R direction, the net force is equal to mv squared over R. Fair enough. Okay, what about M2? Well, M2 is at rest, so it's not really the Newton's second law. It's, in fact, it's equilibrium instead, right? Or Newton's first law if you want, but same thing, right? So equilibrium for M2 looks like this. Well, T2 minus M2G, let's just assume up is positive, is going to be 0. And so that's actually how I'm going to find tension. T1 is T2 and is equal to M2G, right? So the conclusion is that T1 is equal to T2 because it's an ideal string, and T2 is M2G. And I know M2 because the problem defines it. So this is an acceptable answer in terms of knowns. Okay, then we want to find the magnitude and direction of the acceleration of the object in uniform circular motion. So I've used this already, okay, but now I know what T1 is. So perhaps I can use this to get, well, either I get V and then I compute V squared over R, or I directly solve for V squared over R. So let's do this. Let's say T1 is M1V squared over R. Okay, that means that M2 times G is M1V squared over R. So let's just remember, I want acceleration in the R direction, right? And so let's say I'm not being super careful. I'm like, okay, well, I'll just solve for V because I know it's V squared over R. So then V is going to be M2GR divided by M1, all of it square rooted. Right? That's just isolating V and square rooting. And so then I can say AR is V squared over R. Okay, so that would be 1 over R, and then V squared is going to be M2GR divided by M1. So it's going to be M2 over M1G, and as far as direction goes, it is radially inward, or centripetal, same thing, right, toward the center. Okay, so, okay, I mean, that's fine. There's nothing wrong with that. I can do that. Alternatively, if I wanted to be a little quicker, I would say, well, this means that v squared over r, I'll just solve directly for the whole thing. V squared over r is equal to m2g over m1. Because it is a little silly to square root to get v only to then square v again. I mean, like, okay, bummer. Okay, but this would then tell me, okay, well, directly that's AR. It's equal to this. All right, so that's a little faster if you want to do it that way. But okay, that's the centripetal acceleration, a sub r. Then we want to find the linear speed of the object in motion and the time period. Okay. Now, we just found that v squared over r is equal to m2g over m1, right? Now, of course, I mean, it even comes from here, so obviously we're going to get the same answer. So if you did it this way, you can then say, okay, well then v is this, because that's where it came from in the first place. But if not, you say, okay, AR is m2g over m1. That means that this is the case, and then you isolate for v, and that will be the speed of m1 as it goes around in a circle. All right. And then the last question is the period of revolution. Okay, so this one, I never liked this one. I'll tell you why. Okay, first of all, the period of revolution only makes sense if you travel at constant speed, right? So t equals t sub rev is the time to complete one revolution. Okay. Now, obviously, if you're not going at constant speed, it is going to take you a different amount of time every time to complete a revolution. So it makes no sense to talk about a period of revolution in that case. However, if you have constant speed, which, by the way, we have, then it makes sense to say, well, how long does it take me to go around once? Because it will always be the same amount of time. Okay? Now, because you'll see why I'm emphasizing this, because motion occurs at constant speed, we have the following. So not only does it make sense to define a period of revolution, the period of revolution can be written as the distance traveled divided by the speed. And I hate this equation because invariably you've learned this equation in high school, that v is d over t, and so distance is v times t and all of that. And so you know it, right? And it's irreversibly seared into your brain. And it's great as long as speed is constant. But what happens is that after spending 3 weeks on kinematics, where we went through the trouble of saying acceleration is constant, x of t is 1/2 axt squared plus v naught xt plus x naught and all that. Okay, so we went through the trouble of defining all of this 1/2 axt squared plus v naught xt plus x naught for constant acceleration. Now we do circular motion and we're like, oh, time is just distance over speed, and the bad habits kick back in from learning this in high school. And now moving forward, this is, for whatever reason, you're like, fuck it. It just gets thrown out the window and you start doing distance as speed times time or whatever. So kinematics are here to stay. We spent a long time in kinematics for a good reason, so please don't forget them, right? And yes, you may, in fact, say that the period of revolution is the distance divided by the speed, but only because the speed is constant. If there's an acceleration, we go back to kinematics and we do it proper, okay? So, okay, for a revolution then, what is the distance traveled? Well, it is the circumference of the circle divided by the speed. Now the speed, call it v, that's going to depend on the problem. In this case, we know what v is, right? It's this thing. So, the period of revolution, in this case, is equal to 2 pi r divided by the square root of m2gr over m1. Okay, so this can be rewritten, hopefully we agree, 2 pi r, square root of, the square root stays, but you can flip the fraction, m1 over m2gr. You can leave it like that, but if you really want to simplify this, what you would do is you would absorb r under the root. That would get you r squared, and you would then use that square to kill the r down here, and that would be your period of revolution. Okay, so not to oversimplify circular motion, but in the case of this chapter, really the only two new things that we have, or tools that we have at our disposal, are Newton's second law, but in the context of circular motion, so with an acceleration that's v squared over r toward the center, and then period of revolution. Those are the only two new formulas, if you will, that we have to deal with. And what we'll see is that really circular motion is just about knowing how to draw free body diagrams and things that we've been doing before, with the caveat that you have to use the RTZ coordinate system, so you can't just go willy-nilly forget about it and use x and y. You have to use the RTZ coordinate system so that everything is consistently set up the right way, and Newton's second law, where f net r is mv squared over r, actually makes sense, because it's only true in the r direction. All right, so let's do one last one and try to tie it back to things that we learned last week, right? So that, because I just said it's about free body diagrams and things like that. So let's try to make a connection and see what other type of problem you might be asked to solve on an exam. So this one's a classic type of problem. There's variations, but it's super classic. And it's been given on exams a few times in different formats. But you have a woman in a train. The train is traveling along a curved path of radius 75 meters. Let's assume into the page, or coming out of the page, I'm sorry, it says coming out of the page. Okay, so then what we're saying is that, you know, the tracks are doing this, right? Like these are circular tracks, and r here is the radius of curvature of the tracks. In other words, it's the radius of the circular path along which the train is moving, but just like the previous problem, the circle is in the horizontal plane, right? And we know how fast the train is moving, okay? And it's the tracks are not banked, so they're horizontal. They're not at an angle. And she's trying to hold a book against the wall by exerting a certain amount of force at 30 degrees above the horizontal. And we want to know the minimum coefficient of static friction between the book and the wall needed to keep the book from slipping downward. Okay, so let's make a copy of this. We'll bring it down here just to be able to reference it as we go. Okay, but I'm going to draw the free body diagram of this book. In fact, I'm going to start by drawing my axes because I have circular motion. So I know I have to use the RTZ coordinate system. I don't have a choice. All right, so what is the r direction? This is the r direction toward the center of the circle. T is in the direction of motion tangent to the circle, so it's coming out of the page. I don't really need it. There's nothing going on along T. So the other axis that makes sense is Z, just like in the previous problem. And now if I draw the free body diagram of this book has a mass m, therefore it has a weight force mg straight down. It is being held up by a force that we will call F from the woman that is exerted at an angle theta, which is 30 degrees above the horizontal. Of course, it's in contact with the wall, so there is a normal force from the wall. And it seems like the way she's holding it, there's a good chance that this book might not slip, but if you imagine that the book is quite heavy, well, let's assume it's not a book, it's an anvil. Maybe this force isn't strong enough to prevent the book from slipping down, right? If it's an anvil, it's like, oh man. Okay, so it's not obvious that just because the force F is drawn in the proper direction that it is sufficient to maintain the book in place. And in fact, we want the minimum coefficient of friction given this force for which the book does not slip down. Okay, well, if it does not slip down, it is because static friction prevents it from slipping down by pointing up. Okay, so all I did is I drew the free body diagram. Right, that's last week. I could have drawn something like this last week. I had all the tools to do it. The new tools from this week are Newton's second law for circular motion, right? The two equations that I'm going to write, which are going to be F net R is equal to mv squared over R, and then F net Z, which is just going to be 0 because there's no motion along Z, because we don't want the book to slip. So there's no motion up or down. Right? Okay, so then what's the net force in the R direction? All right, well, this one's a little harder, right? We have to be careful. The R direction is to the right. Anything that points to the right counts positive. Anything that points to the left counts negative. Okay, well, to the right, we have all of the normal force minus the horizontal component of F, which is going to be F cosine theta. And that's going to be m v squared over R. And then in the Z direction, up is positive, so Fs plus the vertical component of F, which is F sine theta, minus the weight force, is equal to 0. And if we count our unknowns, we have one too many, right? N is unknown, Fs is unknown, and what else is unknown? Wait a minute. No, that's it. Well, okay, no, duh. It's not apparent. Mu s is unknown. We're solving for mu s, so duh. It's just not in my equation yet because, well, I was going to try to make the point that I have too many unknowns, which I do. I have mu s, n, and fs. And so then I need a third equation to, be able to solve the whole thing. The third equation, hint, hint, based on how the question is phrased, the minimum coefficient of static friction between the book and the wall so that it doesn't slide down. Oh, okay, so the book is on the verge of slipping. So Fs is maxed out and equal to mu Sn, and that's my third equation. Okay, so the coefficient mu s min is, or corresponds, rather, I need to say this, right, to the book being on the verge of slipping with Fs is equal to mu s min times n. If I write Fs equals mu Sn and I do not say that the book, the block, whatever it is on the verge of slipping, I will get slaughtered on midterm 1, which doesn't sound like a good plan. So I need to make sure that I explain that I'm allowed to write Fs is equal to mu Sn because I am on the verge of slipping. Okay, now if that's true, my equations just became a lot more interesting to solve, right? I can now, instead of writing Fs, write mu s min times n. So I'm going to do that. I'm going to get rid of static friction. I'm going to say, well, this is going to be mu s min times n. Okay, so I'm going to find n with the first equation, plug it into the second, solve for mu s min. Okay, so this is going to be n is equal to f cosine of theta plus m v squared over r, and then here mu s min times n is going to be mg minus f sine theta. Okay, so if I plug this into here, I'm going to get mu s min multiplied by all of this is equal to mg minus f sine theta. All right, so conclusion is that the smallest coefficient of friction that we have, or that we need rather, for the book to not slide down is mg minus f sine theta divided by f cosine theta plus mv squared over r. Okay, and we have all the values for this. All right, so mg is going to be 0.25 times 9.8 minus 1.5 sine of 30 divided by 1.5 cosine of 30 plus 0.25 times 25 meters per second squared divided by a radius of 75 meters. This is approximately equal to, with a smidge of rounding, 0.5. Great little question, right? This was actually a problem in and of itself at some point on an exam. Could be a longer problem than this. This one just had one question. But hey, you had quite the steps, right? So, you could break it up and give some guidance and say, okay, write Newton's second law and try to make it 3-4 questions instead of one. But the point is, to solve it, there's a lot of interesting steps, and it's a good problem to tie back to what we learned last week, which is entirely different, and then see how it might be applied in the context of circular motion. Of course, then Newton's second law gets written differently, but in a sense, as different as circular motion is from what we did before, the problems in practice somewhat involve similar skills. So that's part of the reason why it shows up now, right? It'll also be helpful to know a thing or two about circular motion before we start talking about solid rotation when we get closer to midterm 2. So anyway, those are the problems I wanted to do today because I wanted to make sure we talked about all these different things: vertical circular motion, horizontal circular motion, the axes, Newton's second law, period of revolution, all of that. Hopefully this gives you a good overview. Circular motion is it doesn't take a long time to get good at circular motion, right? So if you're kind of a little bit behind or whatever, maybe try to catch up, because this is a bit of a shorter chapter, and you'll be glad you've done it when, by the time midterm 1 shows up, because for sure this chapter is on midterm 1, maybe work and energy, or part of it, we don't know. It depends how fast lecture moves, and if the two professors, try to coordinate and agree on the same coverage. But for sure, this will be on midterm 1. So the 4 chapters, 1D kinematics, projectile motion, Newton's laws, and circular motion, those will be on midterm 1. A lot of the time, if those are the only 4, then you know exactly how many problems you're going to get. You're going to get 4 problems, 1 on each, and there you go. If work and energy is included, or part of it is included, usually you get 4 problems. One of them is kinematics. That could be 1D kinematics or projectile motion. The second one is Newton's laws, usually F net equals ma stuff. The third one is circular motion, and then conservation of energy or work or whatever. So it's midterm 1, the upside is that there's only so many options. You're going to get 4 problems very likely, and so it's kind of easy to know what you're going to get tested on based on the coverage of the exam. So, of course, most of the time it means you're going to be tested on everything, but if you really take a step back, there isn't that much. There's a lot of overlap between the first 2. There's a lot of overlap between the skills from last week and this week. You just have to be careful, when you discriminate between linear motion and circular motion. Be careful with that. But overall, that's what you should at least expect to be tested on those 4, plus or minus work and energy. So hopefully that helps. Thank you for watching, as always. I appreciate it. Thank you for those of you who give me feedback and send me the homework and all that behind the scenes. That is much appreciated. And have a good week. Catch up if you're late on physics. You'll be happy you did. And don't wait till the last minute to study for midterm 1. I mean, I know you have other things to do. I get it. There's a lot of stuff, but if you can start doing physics the week before, you will be a lot happier and a lot less stressed, because physics is not about cramming is the thing. Like, cramming only works to a certain degree. It's much more about understanding what you write and when, and why you're allowed to write this for circular motion versus you wouldn't write the same thing for linear motion, for example, when it comes to Newton's second law. And once you get that, which means you have to spend a bit of time with these concepts, it gets a lot easier to go through these problems and get good at them. And you start to see that in a given chapter, all the problems, they're all the same. Like, really, they're all the same. They look different, they're phrased differently, and I'm not saying that they're all easy, that's not true, but they're all the same in the sense that they try to get to the same equations and concepts because there's only so many. And you want to get to a point where it becomes a little bit easier for you to see that, so that you know how to set up your equations and then combine them to get the solution. Anyway, I'll get off my soapbox. Thanks for watching. For those of you who are signed up, I'll see you later. And have a great week. I'll see you next week.